Welcome to Homework Lib.
This is chapter 35, problem number 22. We're given the distance between the two slits as 0.072 millimeters, and the distance to the screen is 0.8 meters. And also distance from the center of the central maximum to the first minimum is given to us as 3 millimeters. So y here is going to be 3 millimeters. Again, this is from the central max, the center of this, to the first minimum, right? So we're also given the intensity at the peak of the central maximum to be 0.06 watts per meter squared. We're asked to calculate the intensity at points on the screen, 2 millimeters, and at 1.5 millimeters in part B. So if we're asked to calculate the intensity, the distribution of the intensity based on the place on the screen is, the equation goes like I equals I naught cosine square the phase, so phi d y lambda times r. Now, we could plug in for y here 2 millimeters, and d r is given to us. We know what pi is. However, we don't know what lambda is. Lambda is not given. So we need to first find what lambda is. In order to do that, we're going to take advantage of this information here, the distance between the central maximum and the first minimum. Again, this is, as you know, r tangent theta. This information is given to us. Now we can get the information regarding the angle here. Then, since it's the first minimum, we can use it in d sine theta equals, since it's a minimum, 1/2 of the lambda, right? By plugging it in here, then we can calculate what lambda is. So let's do just that. And we're going to take advantage of the small angle approximation. Now, then tangent theta is going to be, by dividing both sides of this equation by r, y over r. So then we're going to assume that this is basically approximately sine theta, and we're going to plug it in this equation. Then what we have is going to be dy over r equals m plus 1/2 lambda. So from here, if we want to find what lambda is, we divide both sides by m plus 1/2, m plus 1/2. Then I'm going to go to a new page here. What we have is going to be, these are going to cancel out. Lambda is going to be dy over r. Lambda is going to be dy over r, m plus 1/2, right? dy over r, m plus 1/2. So we know that this is a minimum, so m is going to be equal to 0 for our case. So d times y, r 1/2. So 2 dy over r. Let's plug in the values and find out what it is. D for us is 3 times 10 to the power of negative 3 meters. This is our y, and d was given to us as 0.072 millimeters. So let's convert that to meters also. So again, this is d and this is y, divided by the distance to the screen. From here, we're going to find our wavelength to be 540 nanometers. So now, since we know the wavelength, we can go back and use the intensity equation in order to answer part A. In part A, our y is 2 millimeters. So we were trying to figure out the intensity, just to remind you, cosine square pi dy over lambda r. So here, the peak intensity was given to us as 0.06 watts per meter squared. Now cosine square, 3.14 times d. In this case, well, it was 0.072 times 10 to the power of negative 3. And then times y is given to us as 2 millimeters. So it's going to be 2 times 10 to the power of negative 3 meters divided by lambda is 540 nanometers. So I converted it to meters. And r was 0.8 meters. Right? So if you do the algebra correctly, we're going to find the intensity at this point on the screen to be 0.015 watts per meter squared. Now, part B is not really different. The only difference is that y is given to us as 1.5 millimeters. So let's see what happens when we plug it in here. Instead of 2 millimeters, this term, instead of 2, we're going to have 1.5. So then again, I for part B, I equals I naught cosine square pi dy over lambda r. I naught is 0.06 watts per meter squared. Cosine square 314 times 0.072 10 centigrade negative 3 meters and 1.5 millimeters. So we're going to do 1.5 times 10 to the negative 3 meters divided by 540 meters. We convert it into meters. And R would be 0.8 meters. Now, if we do the algebra correctly, what we're going to get out of this 0.03 watts per meter squared.